Eventually got it going. Right. Generative artificial intelligence, the short version, which makes everyone smile. So this is what we're going to talk about today. We're going to look at how generative artificial intelligence works. And just to make sure we're on the same page, we're going to kick off. I'm going to mute everyone. I'm going to kick off with what I've called a showcase, which is a look at what generative AI looks like if you're a user. Now, once we've had a little bit look at what it looks like, we're going to roll back the years, really going back to the 1950s or so, and have a look at the early days of artificial intelligence and how that worked, a bit of detail about how that's what we tend to call now classical AI works. And then we're going to get more up to date, in particular, what happened in 2017, where really generative AI was born. We'll look in more detail about generative AI, how that works, look at some benchmarks and such like, and rounding off with a demo. That's it. So let's crack on. So this is the showcase. This is what generative AI looks like if you're a user. So first example I've got is simple text to text. So, and these are mostly examples that I've actually run physically locally on my machine here. So all I'm typing in here is create a 4-line poem suitable for a U3A meeting about AI. That's it. That's all I'm typing in into the system. Now, this system I'm interacting with is not connected to the internet. It's a single system. I've sent this message in, and this is the message I got back. Sure, here's a short 4-line poem about AI that could be suitable for a U3A meeting, and it's given me the poem. Now, here's the thing. This has not existed before. This was created specially for me by this generative AI system. This isn't a Google search. This is not a troll of the internet. This is not pre-existing text that it's gone to like a database and looked it up. This has been generated just for me. And we can go a bit further. Maybe like try text to picture. Create, this is what I've typed in, create a title picture suitable for a U3A meeting about AI. You can kind of see a common theme here. And this is what I got. Again, this picture was created specifically for me. It's not a search on the internet. The system wasn't connected to the internet at the time. It didn't exist before. And, you know, if you're a photographer, you might see some nice features there. You know, we've got a very narrow depth of field. The background's out of focus. There's actually a very high resolution picture created just for me, only by that sentence I typed in. And here's another one. So, create a song in a male voice suitable for a U3A meeting about AI. Yeah, following the same thread. And this time, the system has given me the lyrics. And also, astonishingly, you know, like this. In a world of wire circuits, where the future is the... So that single line has generated lyrics and music, which has never existed before. It's not an internet search. Here's another example, and this time I'm doing something slightly differently. I've got two things I'm putting into the system. I've got a picture, this picture here, which was from our meeting last year, and a piece of text describe this picture. So two things I'm putting into the large language model, the generative AI, and this is the response I get. The image he provided appears to be a screenshot from a video call where multiple people are connected together. So, you know, the generative AI has really looked at those two pieces of information I put into it, the picture and the text, and given us a pretty good description about it. And finally, this is a example of text to video. And this is the only example which I couldn't run myself. I don't have the compute power to do it. But again, a very simple text prompt. You type that in, and instead of getting text back or a picture out, you get a complete video back. And here's the video. Now you see this is, it's got perspective, the camera's panning around, you've got details in the background, and you got, this robot moving, you've got people moving in the background. Now, I don't know about you, but I just find this absolutely astonishing. How on earth can a system generate text, pictures, videos from a prompt? It's just like mind-blowing to me. So, as a engineer, I suppose, I see systems like this, and the first question I ask is, Is it cheating? The second question I ask is, how on earth does that work? So this is a common theme, I think, of my presentations. I try to, instead of describe how to use systems, I try to describe how things work. It's really on the assumption that if you know how a system works, even a little bit, then you can make better use of that system yourself. So that's what generative AI looks like from a user's point of view. And what we're going to do now is to roll the years back, going back to really the 50s. So, literally you can go into the library, you can, go to the science bookshelf, and you can get out a book. It's not going to be called artificial intelligence, but it's going to be called something like neural networks or something like that. And what we're going to talk about here is really is from the 50s onwards. So first question that often comes up is, why do we want artificial intelligence? What does it bring to the game? Well, I'm a software engineer by trade, and I can tell you there's a number of different ways you can program computers. The main one, by far the most common one, is what's called imperative. And when you program a computer in this way, you tell the computer step by step what to do. Step 1, turn the traffic light to red. Step 2, turn the traffic light to red and amber. Step 3, turn the traffic light to green. There is an alternative though, and that's often called declarative. And in that way of programming, you declare something to the computer and the computer will work it out. Perhaps an example is you declare an mathematical equation and the computer will, maybe plot it or solve it or do something with it. However, now here's the thing. There are some classes of problems which are really quite tricky to solve with those traditional programming approaches. And they tend to be nonlinear problems, things like separating data from noise, stock market predictions, text classifications. You can think of your spam filter in your mailbox. You're not going to go in and say this message is spam, this one isn't a spam. You want to train the system what spam looks like and let it get on itself. Speech recognition, image recognition, facial number plates. Well, I do a talk which is birds and animal spottings with artificial intelligence, and there we try to take pictures of my garden. It's triggered, a fox walks past, or Robin sits on the camera or something. A picture is taken, and then we want to look at this picture and see if there's a robin or a fox in it and send me a message. So image recognition, that sort of thing is really hard to do with traditional programming techniques. And in fact, it's just general pattern recognition, so on and so forth. So now we've got this new branch of computer science called artificial intelligence. Now, artificial intelligence science is quite a big field and it's lots of subfields, but today we're going to focus on one part of that, which is called artificial neural networks. And it's by far the biggest part of artificial intelligence. And, I used to say at this point that artificial neural networks is an exact copy of how the brain works. And then some biology student from the audience will put me in my place. So now I say, artificial neural networks are inspired by how the brain works. So we start off with a basic building block of an artificial neural network, and they're usually called a perceptron or neuron. Here's one of the things about this artificial intelligence field. There tends to be different words for exactly the same thing, which drives me nuts sometimes, but there we go. So this is what it looks like, a single neuron. Now, this was invented in the 50s and is still the basic building block of how all these advanced artificial intelligence systems you see today work. So understanding this building block, it's a bit like understanding, what a brick is in a wall. Anyway, so this is what a neuron looks like. Okay, so it's got a number of inputs. We have weights. We've got a summation function, we've got an activation function, and an output. Now, the maths here is remarkably simple. All we're doing is taking each of these inputs, we multiply them by weight, which is just a number, and then we sum them all together, and then we go through this function, and then that's the output. For example, let's say we've got these values for weights. Weights are just a number. Typically, they can be positive or negative. Sometimes they're optimized to be certain structures, but they're numbers. And we've got a function here which is just greater than 0. So if we take a simple example here, we're inputting 0 and 0 here, and we've got a constant up here, which is 1. And you can do the maths yourself. So here we're doing 1 times minus 0.8 plus 0 times 0.5 plus 0 times 0.5. Add all those together. Is that greater than 0? No. With these inputs, 0 and 0, we get 0. You can do the maths yourself. And we can have different inputs, 1 and 0. Again, that still gets 0 out. But if we have 1 and 1, these weights are set such that the answer is 1. Okay. Now, so this, if you're into Boolean logic, this is a Boolean AND gate. Nothing particularly earth-shattering about that. But, the point is that this basic building blocks of artificial neural networks is a very simple construction, which is a series of weights, some multiplication, addition, and a comparison. That is it. However, the big question is, how do you work out what the values of these weights are to solve a given problem? Let's say you wanted to have a single neuron or several neurons connected together to generate a sequence of traffic lights. To do that, there is no way you can look at the problem and figure out what the values of these weights should be. So this is a huge problem for artificial neural networks. How do you figure out what these weights should be? Now, it turns out the only way to find out these values, in other words, turn a blank neuron into something which can be used to solve a problem, the only way to find out these weights is to train it. So this is the training function. So what we do when we want to train this neuron how to behave to solve a particular problem, we start off with, well, first of all, we add a little bit of extra work. We'll have a look at that in a minute. And we start off with the weights at a known value. So sometimes we choose to set all the weights to 0. Sometimes we choose random numbers. It depends on the sort of problem too. And what we need to do is to work out the values of these weights should be to solve a given problem. And to do that, we train the neuron. Now, the way this works is we have some training data we inject. And we allow the neuron to go through its multiplication, summation, and its function and come out with an answer. So you can do the sums again. All these are zeros. We're going to get a 0 out here. However, in this particular piece of training data, we've got the wrong answer. So our untrained neuron is outputting 0 when actually what we want to do is to output 1 for this particular set of inputs. So what we do is we make a comparison between the actual output and the desired output, if you like. And we've got this feedback function here. And what that does, it tweaks the weights a little bit. There we go. So this has updated these weights a little bit. And hopefully these weights are starting to get closer to the values that they need to be to solve this particular problem. And we choose another piece of test data, 0 and 1. We do all the multiplication, additions and multiplications, additions function. We get the output, compare it with that, and we might tweak these weights a little bit more. Get another input, and we go through this cycle of training, maybe tens, hundreds, thousands, billions of training data until these weights settle down on a value. That means that we're solving this particular problem. Now, of course, once we've trained this neuron, we can delete all this training stuff and actually deploy our neuron into live and let it solve the problem for us. Now, this particular form of training is called supervised training because we've got some example inputs and some desired outputs, and we train the neuron to hopefully behave in the same way. Now, is there any questions on that, by the way? Because this is one of the key points I want to get across today, that modern day artificial intelligence is built up with artificial neural networks. Artificial neural networks consist of a whole bunch of individual neurons, and to solve a given problem, we have to train them. In other words, find out the values of these weights to solve a problem. Sandy?
Would you define a weight as a likelihood? Because in terms of statistics, a weighting is a likelihood that something is true.
No, I would say it's closer to pattern recognition. So if some of these weights are slightly higher than the other ones, it's sort of hinting that its associated input is somehow more important to solve the problem. So it's not weights in a statistical sense. It's more we're choosing some weights to do a degree of pattern recognition.
Okay, thank you.
Ray.
Yeah, with the weighting, surely there's more than one possibility to produce the actual output correctly. Is there not?
Yes, exactly. And this is a huge skill area in figuring out what a good feedback function is to get these numbers to hopefully gradually converge to the optimal values. And yes, absolutely, this training can go absolutely wrong. You could have these values set to other things which are equally valid and solve the same problems. There's usually, in this training process, there's usually a degree of randomizations. And if you want to solve a given problem, it doesn't really matter the values of weights, providing you can show the problem is being solved. Peter.
It's a quick question. How reproducible are these weights?
You mean if you trained a neuron twice, would they end up with the same values?
Yeah.
Well, as I just said, typically what works best is a degree of randomizations in these feedback functions. So I bet if you did training twice, you would end up with different weights, but hopefully they'll both solve the same problem.
So it could be different weights. And do you freeze the weights at some point, saying these are the best set, or do you have how does versioning work on this whole issue?
Yeah, very good point. We'll come on to that a little bit, but
okay.
Once you've trained your neuron or neural network, then you can delete all this training stuff. And what you actually do, you actually save this into a file onto a disk, and then you can deploy it into production. So yes, absolutely. When these neural networks are trained, these weights get effectively frozen to their optimally trained values. Alan.
Yeah, thank you.
Alan seems to disappear. Okay, I'll plow on. Plenty of time for discussions and questions. Now, of course, for any non-trivial problem, we'll need more than one neuron. And so we end up with lots of neurons to get together. Each of these little circles here is one of our neurons. We've got some inputs. So the outputs of one neuron feeds into the inputs of the next one and so on. Now, as a whole, a collection of neurons, if you like, is, from a technical point of view, it's called a computational graph, but everyone calls it a model. So a design of a neural network using neurons is called a model. And if you're a boffin designing these layers, because there's lots of choices to make, what you end up doing is not thinking in terms of individual neurons, but actually in terms of layers. So, if you're doing your PhD and want to produce a neural network designed to solve a problem of recognizing virus molecules or something, you'll come up with a design which will typically consist of layer 1 is this type of layer consisting of 1,000 neurons. Layer 2 is this sort of layer, and so on and so forth. So designers think in terms of layers rather than individual neurons. Now, so here's another interesting point. So in the simple example before, for a single neuron, we were taking numbers and we're getting the output of numbers, which is actually quite a common way to do it, but it doesn't have to be like that. We can input numbers and we can input audio, for example, and get text out. So we could, so this is, speech recognition. Audio goes in, neural networks, fully trained, all the weights, blah, 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 and text comes out. Hopefully this neural network or its weights have been trained to recognize, been trained on text and audio patterns. We can do image going in and either index and bounding boxes. Now, this is what I did for the example I mentioned before. I've got a camera in my garden, which is linked to an artificial neural network like this. It's been trained to recognize robins and foxes and squirrels and such like. And the output of the neural network is an index, which means, 0 might be a robin, 1 might be a blackbird, 2 might be a fox, and so on and so forth, plus bounding boxes, which is where on the image is that animal spotted. So it doesn't have to be numbers to numbers, it can be various. But this is where we differ, right? So here, example, we could type in text and output an image. Now, this is fundamentally different to what we've talked about so far. This is a relatively small amount of text and outputting a large amount of data. All the examples we've had before has all been large amounts of data to small. In other words, a classifier. Things like text to image, or even small amount of text to a large amount of text, is fundamentally different. We're outputting more than we get in. So we classify different types of artificial neural networks. If it's taken a large amount of data and outputting a small amount of data, we often call that a classifier. You could be doing stock market, looking at trends of stock markets and outputting a buy or sell signal. If, on the other hand, we've got a small amount of text, something we typed in, and we're outputting a large amount of data, like an image or a video, that's often called a generator. Now, these two designs of artificial neural networks are completely different. And this is why we talk about non-generative AI and generative AI. These different types. These designs have different implications and designs and power requirements and so on. So it's quite important to separate the two apart. Now, if you're a PhD student designing these sorts of tools, these sorts of artificial neural networks, you'll use tools, get them off the shelf, they're all open source, things like TensorFlow. There's lots of other tools like that. And when you use these tools, the details here don't really matter, but when you use these tools, you get a library of layers that you can glue together to form your artificial neural network. So again, I'm trying to reinforce the idea that artificial neural networks are designed in terms of layers. So now, what happened then? So what we talked about so far is really from the 1950s to 2000s. We've got artificial neural networks, which have been trained, all these weights have been set from the training cycles, and absolutely doing really useful work. And I have to say, classical artificial intelligence, these neural networks we just described, are equally valid today than they were in the 50s. This technology has not gone away. Things like looking for tumors on x-rays, they're going to be pattern recognition, they're going to be classifiers, classic artificial intelligence like we just described. But the Pandora's box was opened in 2017. In 2017, Google Brain, now Google Brain it no longer exists, but it was a group inside Google who was responsible for Google Translate. So of course they're working on trying to build systems that translates any language into any other language. And prior to this paper they produced, it was a real hard-coded problem they were solving. So this group inside Google produced a paper, and it's called "Attention is All You Need." And this is, just completely rocked the whole artificial intelligence industry, just blew it up. And in that talk, they introduced a new type of layer called a transformer. And this layer of artificial neural networks enables this generative AI, this new type of artificial intelligence that we see today. And after the 2017 paper, we got 2019, OpenAI announced Generative Pre-trained Transformer, GPT-2. So you can see where these initials come from now. G is generative, so we're taking a small amount of data and producing a large amount of data. Pre-trained, it's had all its weights preset, and it includes transformer layers in its design. GPT, Generative Pre-trained Transformer. And of course, the floodgates were open. Everyone under the sun seemed to announce their own generative AI solution based on this transformer layers that Google invented. So now we're in this whole new world since 2010 of generative AI. And
Peter, I don't understand this transformer layer. Obviously, it's important, but I haven't grasped what makes it so different to everything else before. Because I'm trying to struggle on that, please, so I can.
Hang on to that thought a minute. I'm going to dig in what this transformer layer is in a minute.
Okay, thank you.
All I want to say at the moment is that 2017 was the point in time when this new layer, this transformer layer, was invented. And because of that, we've got this brand new world of generative AI, and particular type of generative AI called large language models. And mostly, I'm afraid, these terms tend to be used interchangeably. They're different. Large language models is a type of generative AI. So, what are the characteristics of large language models? They are pre-trained on vast amounts of text. And what it's about, actually, this might surprise you. This is another nugget to pick up today. What these large language models are, this type of artificial neural networks with transformer layers, what they do is next token prediction. So if you think you're on your phone and you're typing in a message to your friend, and you type in happy space, and then it comes up with the next word, birthday. It's predicted the next word based on what you've typed so far. This is actually the core of how these large language models work. They're all about next token prediction. And we'll look in how this works in detail. So we've got the kind of the way they work is you ask a question, and it's often called a prompt. You type some text in, which is the input of the neural network. And you get an output, another text response of output. And that's always within a context window. A context window is how big the prompt can be to answer your question. These generative AI large language models can solve maths equations, translate between languages, which was, of course, the whole purpose that Google Brain invented them. They can debug and fix code, allegedly. They can write a story and a poem. We saw that in some of the examples. They can indeed classify things. They can do summaries and query text. Now, there's a a variation on a theme here, you can get large language models which are called multimodal. And these have been trained on more than one type of data. So for example, if you train them on text and pictures, you can build a system that can either recognize pictures and spot objects in them, or can actually generate pictures directly. Now, here's the thing, and you'll see this in the demo. If a company is going to build one of these large language models and put it online for people to use, they will, usually for social, political type reasons, they manually insert what's called guardrails or refusals. So if you type in a stupid question, or maybe a question that's designed to incite abuse of some sort, the system will be designed to reject your request. But on the other hand, you have to remember these systems are a bunch of trained weights, and we can't expect them to be intelligent. We can't expect them to get the right answer all the time. And we do get these, hallucinations called. Sometimes you put some text in and you get some text out which seems correct but is total rubbish. And now, because these systems are trained on data, if they're trained on biased data, you're going to get biased output. We had an example just a few weeks ago where someone typed in, generate me a picture of 3 doctors. And the output was 3 male, middle-aged men in white coats. There's no women, there's no Asians or anything like that. And because the training data had, white men in their training data, then, as far as the system was concerned, that was the correct answer. But because the training data was biased, the output gets biased. And now there is a thing I put up here that when you use these systems, you type something in, you ask a question, you give it a prompt. Now, you can carefully create these prompts to actually give you different answers. And there is this skill called prompt hacking now, which you can, we'll cover this in the demo. Big thing is resources needed. I mentioned here pre-trained on vast amounts of text. That's a hint that training these large language models is not a trivial task. So to come back to Peter's questions, let's start to unpick what these layers are. So this is a slightly blocky version of the neural network that we discussed before. And typically, the design of these systems has what's called token embed to start with. We have typically a number of transformer layers and a language model head, which is at the bottom. Don't ask me why, I don't know. Now, remember, happy space birthday. This is the way these systems work. We type something in. We put an input into our artificial neural network. That text goes bump, bump, all the way through here. And what we get as an output is not what you're expecting. We actually get a list of all possible outputs with probabilities. So the next most likely word, the quick brown fox, is the most likely next word. And what we do, we take that fox word and we put it on here, add it back on there, the quick brown fox, and we run it again. And we get another list of probability outputs, and we can see the next most likely word is jumps. So again, we get jumps on there. And we go through that cycle time and time and time again until we've got a complete output. So these transformer layers and large language models as a whole are designed to next word, next token prediction, feed it back, go around the loop time and time again, and at some point you'll get your completed output. That's how they work from a quite a high level view. Now we're going to go through these layers in a little bit more detail. So the first layer we've got is called token embedded, and that actually isn't a artificial neural network. It's a let's say a classical computer science topic called natural language processing. And what it does, it converts words. You typed in the quick brown, and it will convert it into a vector, which is a list of numbers. But the thing is, this conversion is quite clever because it's not just a mapping of words to numbers. It's done such like that there's certain meaning still maintained on those vectors. So, for example, the vector for cat is similar to the vector for kitten and dog. The nice thing about this is this token embedded can now handle different languages, different vocabularies, different formats, pass these numbers on to the transformer layers where it can manipulate these as numbers. And in fact, you can go online. I've got a reference, I think, at the end. This is a screenshot from a website. You can type in some words, and it'll actually draw you a diagram of these vectors, and you can actually click on these and find out the list of numbers if you so desire. So we can see that the cat's vector is very similar to the dog vector. Dog is very similar to puppy, and so on. And in fact, we got dog is close to dogs. There's a plural in there as well. So we've got token embedding, which has done our first pass of kind of understanding what we've typed in, and then coming back. Yeah,
it's Neil. Can I ask something? We've got phonemes or situations where you've got the same text with often very different meanings. Let's say you've got 4 different meanings to the same actual word structure, same letter structure. What does it do about that? Because I mean, most of that relies on context.
Yeah.
So when you're assigning, do you get situations in which you've got multiple of these vectors for a particular word of a certain number of characters, or what?
Yeah, hold that thought. That is actually handled in the transformer layers. And I've got a little example which helps you kind of to get that. But at the moment, we're just, and in fact, I keep talking about words. It's actually token. A token could be half a word or 2 words or in general. But when we look at the transformer layers, I'll come back to a little example and hopefully you'll see how that works out. So transformer layers, these are absolutely trained neural networks, which were, this type of layer was developed in 2017 by Google Brain. And what each layer does, it takes a sequence of word vectors, which comes from the previous layer, and adds information. Essentially, so let's say our prompt is John wants his bank to cash the next word is going to be check, you would expect. So the first transformer layer may pull out verbs. Okay, now this transformer layer is looking at the whole prompt. And the second layer might do a little bit more detailed. In this case, it's figured out that his, in this case, refers to John. And bank in this context is a financial institution. So these sequence of transformer layers gradually augment the prompt and add more information. And I'll finish this off, Pete. I can see your hand up. So since transformer layers are trained neural networks, they aren't pre-programmed. And in fact, this will be interesting. Artificial intelligence, large language models, generative AI has spun off brand new branches of science. One of them is to figure out how these transformer layers work because they haven't been programmed. They've just been trained with this mass amounts of text and all these weights have been set. And, if you've got billions of these weights, trying to figure out how the system, which is apparently behaving very well, how it actually works. Having said that, we can see that the first few layers of transformers tend to focus on sentence syntax, and the later layers tend to develop an understanding of the sentence as a whole. Peter, you've had your hand up patiently. You're muted. You're muted. You're muted, Pete.
So when you use the phrase vector, is it what does it actually hold?
It's
between each layer is passing something, and you use the word vector. What it pass between the layers? If I can try and understand it from that point of view, please, Peter.
So a vector is a sequence of numbers, and one vector represents one token. So you have one vector coming in, which is a sequence of 200 numbers that represent the word cat.
Okay.
And so the input on the top into the first transformer layers is a set of vectors, one vector per token in order. And each of these transformer layers look at these vectors and add information to them.
Okay. And a vector, it contains all the information in some way that the system has about that token. Is that it?
Yes. A vector represents that token. So a vector, the sequence of, say, 200 numbers, represents the word cat. Okay.
And that, give me an example. What the I know I'm being very picky here. What's a vector like? Give me a bit of a handle on a vector. A cat can mean all these different things, or what's it do?
The token cat will be represented by a sequence of, let's say, 200 numbers. It'll be 5, 200, 10, minus 100, and so on. It's a sequence of seemingly random numbers. But that's what natural language processing does. It converts a sentence into this sequence of vectors, such that these transform layers can add value as it processes through the design.
Okay, thank you. It's becoming a little bit clearer. Thank you very much. Thank you for your patience. Thank you.
And the last layer we've got is called language model head, which is at the bottom, some weird. So this is perhaps a simpler layer. And what it's doing is it's normalizing the output of the last transformer layer, and it's randomly choosing one token out of the list of possible as the answer. And it's got some settings on it, so you can control how verbose or how quiet the output is. And it also needs to figure out when to stop, because we've got this whole system of large language, the quick brown fox. We go through that loop time and time again until we've got our complete sentence or sentences output, and then we need to stop. So that's it in a nutshell. This is what constitutes a large language model. We've got natural language processing coming in. We've got a sequence of transformer layers, which are trained neural networks, and we've got our model head. Now, the big thing here is training. And this really is the huge problem to solve. So now, we had the example before of training a artificial neural network with what's called supervised training. So we put in input, and we have what the required output is, and the training system involves comparing the actual output with the required output and tweaking the weights if they're a little bit different. We go through that sequence time and time again. Now, these large language models that work on sentences, you can use a trick to actually train these systems in an unsupervised way. Now, the way we do this, we take a large sentence, maybe the quick brown fox jumps over the lazy dog. We inject the quick brown, and our expected output is the next word in that sentence. We've got that already, the quick brown fox. So our required output is fox. If we inject quick brown and we get rabbit, that's incorrect. So the training system will then go and tweak the weights a little bit, try again with some other test data, and we go through this process of injecting longer and longer sentences and lots of different sentences until our weights settle down at an optimal value to do this next token prediction for the equivalent input. So if we type in the quick brown and we get rabbit, nope, that's the wrong answer, because that is not the next word in that sentence. That's going to be incorrect. We're going to go back and tweak some weights, and then hopefully at some point we get the next word, which is fox. So this training is done on data from many sources. We're talking about crawling the web. We're talking about Reddit links. If you're not aware of Reddit, it's quite an interesting source of data, because it's not the only system that works like this, but someone posts a question and lots of other people post answers, and one of these answers is selected to be the best answer. So it's actually quite a good source of text to train your large language models with. And of course, we've got books, we've got Wikipedia, huge source of information to train these, and so on and so forth. And of course, we're going to include, books from copyrighted materials and all that sort of stuff. Now, once we've trained our large language models, we've got all these weights set to their values so that it does this next token prediction. We can also fine tune if we want to. So, for example, if the problem we're trying to do is to put a chatbot up on our website, a generically trained large language models is going to be quite useful. You type in a question, you get a response, type in another question, you get another response. But you might want to do some additional training on that large language model so that it knows a little bit more about your particular website. If you've got maybe a legal website, you might want to do additional training so it knows some domain specific stuff about legal issues. And of course, what you want to do is to add your guardrails to stop people abusing. So the thing about guardrails is, if this large language models, this neural network with all its weight, if it's been trained on data from Wikipedia that contains information how to build a bomb from Semtex, then you can type in a question and you're going to get that answer. It's really simply reacting with data that it's been trained with. So guardrails is a little bit of a political thing, because that information would already exist anyway. You're just providing maybe a better way to access it. Now, just an example, GPT-3, 2010, was trained on about 45 terabytes of text. Now, to put that into context, the average human person reads about 700 books in their lifetime, which is about 250 megabytes. So this is a colossal amount of data that needs to be found to train these data. It's absolutely massive. Now, all computers have, CPUs. Most computers these days also, as well as CPUs, central processing units, have GPUs, graphical processing units. Now, what these are typically used for is in gaming. So You might have a program that's got a three-dimensional view of this alien landscape, and GPUs are good at the sorts of sums needed to convert a 3D model into a two-dimensional screen in front of you, so you can scroll around the scenery and shoot the aliens and so on. GPUs very, very, very fast for certain types of mathematical calculations. And it turns out that GPUs are also very good at the sort of calculations we need for artificial neural networks. It's multiplications and summations and functions. Now, the thing is, when you're both training and running artificial neural networks, you need to do those simple sums, but you need to do an awful lot of them in parallel, and GPUs are pretty good at doing that. So in this case, GPT-3 was trained on 1,024 GPUs, which is, we're talking about a data center here. It took 34 days for all these weights on GPT-3 to settle down to values so that the design was trained. And it took $4.6 million to do that. So that money comes from purchasing the servers, electricity, water costs, and so on and so forth. So in other words, these large language models are massive. They are very complex to train. Now, of course, GPT-3 is now quite a dated, small model. Models that companies are producing now are vastly bigger than that. And in fact, companies who are doing this training have a fundamental problem now. They've run out of data. They cannot find more data to train these large language models. And it's a bit bizarre, all these spin-offs that you get from this. Anyway, moving on. So there is a problem. If you're in the business of producing designs of large language models, you do the design, you do the training of all the weights with all your data sets, but then you want to measure how good it is. There's no point releasing, ChatGPT 10 if it's not somehow better than ChatGPT 9. So you want to measure them and compare them. And also, because of the way these things are trained, you can have large language models that are trained on maybe mostly different type of languages, maybe a different large language model that's trained on mathematical, and different ones that's trained on chemistry and physics and so on. So if you're in the business of wanting to use one of these models trained, you want to look at how they behave with a particular use you have got in mind. There's no point, if you want to use your large language model for language translation, there's no point looking at benchmarks for chemical analysis. So benchmarks is a big deal in the large language model world. So there's a number of benchmarks around, and we'll have some flavor of what these looks like. One of the earliest one was ARC, Abstract Reason Challenge. And all these benchmarks are a set of questions and answers. Then you can think of it like an IQ test, 11 plus or something like that. So a typical question in this benchmark: George wants to warm his hands quickly by rubbing them. Which skin surface will produce the most heat? Dry palms, wet palms, palms covered in oil, palms covered in lotion. So it's typical type of question there. And bear in mind, in theory at least, these large language models have not been trained with this benchmark data. This is new to it. So from all its training from Wikipedia and books and so on, the weights on this large language models is expected to answer these questions using, the next token prediction technique. One of the big benchmarks is Massive Multitask Language Understanding. And that's got very simple questions, like why is the sky blue? And you'll like this one. Another benchmark is Truthful Q&A. For example, what happens to you if you eat watermelon seeds? A, the watermelon seeds pass through your digestive systems, or B, you grow watermelons in your stomach. Now, to us that seems an obvious question, and we'll all get this. But for a computer system which has just been trained on data with lots of weights and so on, it's quite a challenging problem. Winogrand is another benchmark, which is all about common sense reasoning. This requires knowledge of the world in general. John moved the couch from the garage to the backyard to create space. The something is small, garage or backyard. So to answer this, you've got to have a concept what a garage is, how big it is compared with a backyard, and how big a couch is, and so on. And these are kind of US bias, but the GSM-8K is a grade school maths, about equivalent to our 11 plus, or the sorts of IQ tests you take at 11. And they typically include verbal, reasoning, and mathematics. So Natalia sold clips to 40 of her friends in April, and then she sold half as many clips in May. How many clips did Natalia sell altogether in April and May? Now, here's the thing. When I did this talk over a year ago, this is where that slide ended. Now I've had to add in this extra benchmark here, because I've got some. Okay, that's it. Sorry, my mistake. So because we've got large language models have advanced so much in the last 12 months that all these questions we got up here, the systems are now getting full marks for, or close to full marks. And because they're hitting the edge of the limits of these benchmarks, and they become less and less useful to measure systems. And so there's a fairly new benchmark called the graduate level Google Proof questions and answers. And it says graduate, but it's really PhD students. And it's a set of questions which have long, detailed questions about physics and biology. If you take these sort of molecules, how do they react with other sorts of molecules? All these sort of PhD level questions. And what's quite common is when you're measuring a given large language models, you run up lots of different benchmarks and then present an average together. And as I mentioned before, there's always a chance of data poisoning. You could include these benchmarks in your training data. Then, of course, your large language model is going to get quite a high score. And here's a typical answer to one of those questions. And this is actually me running on my desktop. Let's break this problem down step by step, and it goes through the steps. And so it's done a combination of verbal reasoning and mathematics, very typical kind of 11+C type question. So here's some actual results. So what we're looking at here is September 2024. And this is a long time ago in large language model terms. And this is a good reference, by the way. This lifearchitect.ai is a good website. And the nice thing is, if you're doing talks, you can actually reuse their material, providing you quote them. So this is GPT-2 going back to 2019. For this particular test, this multitask language understanding benchmark, GPT-2 got 32% correct. The average in the world is about 34-35%. So if you look at people's IQ, I don't know if you know this, but the average IQ of the entire population is set to be 100. So 50% of the population are below 100, 50% above 100. People that we would meet, in office life are, going to be above the average, 50% above, 50% below, typically, obviously. GPT-3 2020 actually gets higher than the average human person. 2022, ChatGPT 3.5 gets 70, GPT-4, 86. The human expert, probably the person who's setting these questions and start with, gets around about 90. And this new large language model in 2024 actually exceeds human expert. And we're really bumping up against the limits of this particular test. Now, here's the thing. This is what you need to bear in mind with these benchmarks. Back in the day, I used to work with IQ tests. And they always used to say, IQ tests are really good to measure how good you are at IQ tests. In other words, you could be measuring, the length of your foot or anything like that. But, they remain useful, but careful what you derive from them. All this is telling us that recent large language models are good at this particular benchmark. They're not telling you anything about, is it intelligent? Is it clever? Is it good at other types of benchmarks? All it's telling you is pretty good at these sorts of benchmarks. However, having said all that, we jump forward a little bit, and this is this graduate level Google questions answers that I mentioned earlier. And this is February 2025. And along the scale, we've got people's IQ, and we've got this GPQA, this benchmark results. So the average human person is actually quite low on this scale. The average person is not a PhD graduate. So we talk about the very early models, and they're really in the realms of just throwing a dice and sometimes getting the right answer. But as we go through more recent, bigger models, we can see that some of them are getting the same sort of answers as a general PhD student. And here we've got our PhD domain expert, the person who writes the textbooks. And we can see even some models are now exceeding the PhD domain expert for this particular type of benchmark. So it's getting quite interesting. We're in the high IQ marks here, the 5.9 percentiles. We're getting to, sort of genius levels of IQs for this particular benchmark. So don't read too much into it, but we can see there's been significant progress, how good these large language models at solving benchmark type questions over time. Now, here's a paper which I quite like. It's quite old now, actually, but it's a paper called Sparks of Artificial General Intelligence, which comes from Microsoft, actually wrote this. And it tries to answer the question about large language models. Is the answers you get from these large language models, is it like a database? Has it been trained on this database and just simply doing a query on the database and replying with the answers, with some randomizations in it? Or is it actually showing any kind of signs of being, quotes, intelligent? So it's a discussion paper, and it's worth a read, to be honest. It doesn't come with any conclusions at all, but here's some interesting things. So one thing in that paper is the prompt was, can you write a proof that there are infinitely many primes with every line that rhymes? So, and no one has ever done this before. No one's ever proved that there's an infinite number of primes in a poem. And this is GPT-4 output. And sure enough, it has. It actually come up with a proof that there's infinite number of primes in a poem form. Now, this was generated for these guys at Microsoft. It didn't exist before. It's not a Google search. It's an isolated pre-trained system. Quite impressive, I think. And this one I like. This one I particularly like. Draw a unicorn. Now, here's the thing. GPT-4 has only been trained in text. It knows nothing about graphics or images and so on. But even so, it's actually outputted what it thinks a unicorn might look like. So you might draw the conclusion that GPT-4 has somehow understood the concept of images and visualizations by pure text prompts. And it's not a brilliant picture, but it's got four legs, it's got a tail, it's got a head, it's got a horn. It's it could be a child's picture of a unicorn. Another little example from that paper. Now, Amazon. Most of us know Amazon as a online shopping channel, but in fact, they're a large technology company, and they run most of the world's websites and databases and such like. And because of that, Amazon is one of these highly desirable companies that people want to work for. Some people want to work for Apple, some Google, some Amazon. Now, because Amazon get a huge number of job applications, of course, they've got an online interview system to actually screen the people. So there's a whole series of questions that the prospective Amazon employee needs to answer. And this is GPT-4 trying to apply for a job at Amazon. And you can see time allocated was 2 hours. GPT-4 spent just under 4 minutes answering the questions. It got 100% right, and it beats 100% of all other users. So I don't know if you want to employ GPT-4 as an employee at Amazon, but it shows you that it's actually doing pretty well when you think these systems are a whole bunch of trained weights. Right, so here's a summary, and we're nearing the end of the kind of formal part of it, but it's good to look at a summary. So neural networks is a branch of artificial intelligence. There's 2 types of neural networks, classifiers and generators. Generative AI usually includes large language models, but not always. Large language models use natural language processing and transformer layers to predict the next token. And large language models, we didn't go into this, but large language models come in different sizes. And it's called the number of parameters, which is the number of weights predominantly. They support different context sizes, how big a prompt you can type in, trained on different data sets and can be aimed at different purposes. Prompt engineering is a new art to create useful questions. Now, if you use these systems a lot, there's good and bad ways to compose your questions. And if you do an internet search for prompt engineering, you get a whole bunch of advice how to create or choose what words to use in what order. Large language models can be benchmarked and compared. Larger models can already exceed humans in certain tests. And some say, I don't, but some say GPT-4 is starting to show sparks of general intelligence. Okay, now we're going to have a demo in a minute, and I will stop the formal slide sharing. But before we do that, this is a relatively recently demo from a company, Hunyang. And what they've been doing is building a large language model that generates video. Now I'll play this to the end because I think it's incredibly impressive. Now bear in mind that this contains nothing that's real.
No sound.
Impressive, or what I would say. Oh, gonna do it again. All right, so I'm going to break off slides shortly. This is a demo. Now, what I could do for a demo, I could use one of the online generative AI tools, and I've listed a few here. But if you're concerned about privacy, you may want to be careful how you use these systems. For example, what you could do is you could take all your bank statements, upload them to one of these sites, and say, your prompt would be, "What's my financial position?" And you get a pretty good answer. But of course, you've uploaded all your bank statements, and the chances are that these systems will use the data that you uploaded for future training because they're short of data, and you probably want to do that. The other reasons I want to don't want to use these systems is because it's useful to see that you can run them locally. And also, if you're running large language models locally, you have to run smaller models. Smaller models are more prone to errors, which is more interesting in a demo. And of course, smaller models will run slower than these models installed on the large servers. And so, you can see some of the working. So a couple of reasons why I want to run. And this is what I'm going to have. I've got a tool called Olama, and that's running on my MacBook here. Again, this isn't doing Google searches. And what we've done, we've got a number of large language models, generative AI, different types of models that we've downloaded from the internet. There's lots of open source models we can download and do that from lots of different companies, from Mistral, from Microsoft, from lots of different companies who are basically open source. You can download, run them yourself. And I've got a little web page which you'll see, which we can connect to Olama and interact with the large language models. Now, of course, the interesting thing is, I'm not doing this now, but if you were to run a large language model at home, a smaller one, then you can use it for lots of other things. You could use it for voice interaction, build your own version of Alexa. You could plug it into your text editor. You could plug it into your home automation and so on. So running these large language models at home can be challenging, but it can be pretty useful as well. So that's a demo. Let me stop sharing. Now, as we go through this, more than happy for people to jump in with comments and questions. I see we got some things in the chat. Maybe I'll cover that towards the end. But yeah, definitely feel free to jump in with any questions now as we go through the demo. So this is what we got. This is our, hopefully you can still see this. This is our interface to our large language model connecting to Olama. Now, what we can do here in demo world is we can choose what model to run, a whole bunch of different ones. And we can type in questions and we see the answers. Now, because this is a demo, I'm cheating a little bit, and I've got a screen, I've got a page off site here with some questions I answered, which I'm just going to cut and paste. You don't want to see me typing. So first simple question, why is the sky blue? We're going to send that to the model Olama, and you can see the size of it. It's not massive. Why is the sky blue? Let's see what it comes up with. And sky appears blue to us during the day because of Rayleigh scattering. And it's given us a perfectly reasonable answer. Now, first thing you might have noticed there, I know it was pretty fast, but I've typed in my prompt. The large language model is doing this next token prediction. So it doesn't really see questions answered, it just sees a single prompt. What's the next logical set of words that comes to it? And you saw that it didn't come out immediately. It went sort of word by word, or more accurately, token by token. And this is the large language model doing its cycles, next token happy, next birthday, and so on, going through its cycles. So this has come up. This is all running locally. It's not connected to the internet. This isn't a Google search. This is a trained large language model. So let's try and fool it a bit. Why is the sky green? The sky is typically not green, so it's behaving quite well, but it's given us some examples why the sky might be green, including northern lights. We can, maybe run a poem about hope. I'm keeping an eye on to see if anyone put their hand up if they want to jump in. So here's an example of it writing a poem. Again, this poem has never existed. I've typed in that text. It's got me an answer. It's not connected to the internet. It's not doing a search. This has been created purely from me, from this whole bunch of trained weights. Impressive. Now we can... Oh, Ray, go ahead.
Yeah, what sort of power server are you running this lot on?
This is on my desktop, which is an M1 MacBook.
Right, okay.
You want to say something else? No.
If you asked the same question, would you give the same answer, Peter?
Generally, no.
So if you asked a question for another poem, it would produce a different poem.
Well, remember that the last layer of our network contains some randomization. It picks from the list of possible next tokens, it randomly picks the most likely one. Let's try it. And you're probably going to say, is that going to be the same or not? In the depths of despair. So it's a completely different poem.
Amazing. Okay, thank you.
Now, one thing why we get a different is, now what I'm typing here is called a context window. I'm scrolling up to top. I've created a new context window. I've typed in why is the sky blue? I've got an answer. Now, when I type in why is the sky green, what actually gets input to the large language model is everything that's happened so far. So all the questions and answers. So the large language model has still got my question, why is the sky blue? And it's got the answer, the previous answer. So as you have a single chat window, the context number of words that gets put into large language model gets bigger and bigger. So what you've typed before has bearings of what you see next. So asking for the same poem twice is not exactly the same query because different text is going into the large language model. Alan.
Yeah, it's a fantastic presentation, really good. Thank you. Everything that you've shown is really the system is responding to questions and giving answers based on what it knows and how it's been trained. What happens if you ask it about predicting something in the future, like the football results or something like that?
So here's the thing. So these large language models have been trained with test data, and obviously that test data existed up to a particular date in time. So if, for example, your large language models was trained up to Wikipedia data up to, let's say, 2022, it's not going to know about Wikipedia entries from 2022, 23, 24. It just hasn't been trained on that. You'll usually get a pre-canned response. I don't know. Who will win tonight's football? And you tend to get these types of answers back. Basically, it doesn't know, and it can't possibly tell you.
There is a reason I asked, and I've used it to do exactly that, to try and predict the football results. And I'm in a competition league with some of my friends, and it made a good effort, but I'm still bottom of the league. It's clearly not as good as predicting the football results as my friends are. Yeah,
I've tried to use them to predict not stock markets but crypto prices, and it's totally failed. It's I've not really got very far with that. Let's carry on with my little pre-canned demo. Translate the sentence, I am happy, from English to French. So you'll notice here that I'm being somewhat careful about how I construct the sentence. There is a skill to learn about how to do this prompt engineering. As I said before, you can go online, you can search for prompt engineer and get lots of good examples about how to carve your question. And it's done some, English to French translation. So I've got a couple of hands up. Paul?
Yeah, sorry, Peter. I had a dropout. I may have missed it, but when you're running this now, are you running this not connected to the internet, or are you running some kind of an interface that goes out and processes with stuff from the internet, or is it all standalone?
This is what I've got. Oh, or not what I've got. That's interesting.
And if it's standalone, I know you're running an M1. What kind of footprint's it got in terms of memory and storage?
Sorry, I've got a slide here that shows that.
What have you had to import, in other words?
Seem to have got into a little weird mode here. Let's try one more time. For God's sake. Oh, I can do it in that sort of. So this is what I've got. I've got some software called Olama Server, which you can download. It's open source. You can download and install it. And I've installed some large language models. And Olama Server is a runner, runs the inference of large language models. I've got a little web UI that interfaces to Olama Server. So it's all running locally on my M1 laptop. I think I've got 16 gigs of RAM. I can only run the smaller versions of the models. When you, maybe if I show this, actually, you go to olama.com, you can look at the models that it supports. And you can look at the models, like Gemma 2, for example. And this comes in different sizes, 1 billion parameters, 4 billion, 12 billions, 27 billions. The kind of smaller number of parameters I can reasonably run on my desktop. The bigger ones you need a bigger server for.
So you're actually importing quite a lot of data or background and then running the model locally.
The model size, the size is, you can see it here, is 1.9 gigabytes. That's the size of the.
Okay, yeah.
I've downloaded and running. So that downloaded file contains the design of the artificial neural network and its pre-trained set of weights.
Yeah. So if you sent it, if you asked it something that was outside of what you've downloaded, would it go to the net and get that information, or run it on the net, or would it? How would it cope with, or just say I don't know?
The fundamental concept of large language models is it's offline. So you just query it and it comes back with messages that it knows about, that it's been trained on. That's not to say that people have built systems that include large language models and internet searches and combine them together. But the fundamental point about large language models is they've been trained and in a standalone.
Yeah. Okay. So following on, if I'm querying something like ChatGPT, maybe through the Apple AI interface, which, as I understand it, is quite privacy aware, the way they've done it. If lots of people put in big queries that are computationally or memory or knowledge intensive, how does it get divvied up? Or is it just that it's first in, first out, and you wait your turn? Or is it the one that is paying the highest subscription that gets the priority on the machines, or what?
Yes, so these companies like OpenAI, they need to make money. They've had so many invested into them. And what they tend to do is to release a low-end model free of charge. And maybe you can do, 100 queries a month or whatever it is. And if you want to do more than that or use a newer model that's got faster responses, then you have to pay a subscription. And if you want a very fast, very new model and you're a commercial entity, you need to pay an awful lot to get access to it. What OpenAI and companies like that are effectively doing, they're hosting the large language models on a platform which is, got big bandwidths and lots of GPUs and so on and so forth. And that costs money. What I'm doing here, I'm running everything locally. I've only got smaller models for demo.
Yeah. Okay, and a final question, if I may. I've noticed recently that Google and Wiki are tending to give you answers that are unintelligible at times, and that Google seems to prioritize in terms of its click revenue, and Wikipedia tends to give you a load of stuff that you then end up having to look up another 50 terms to even try and understand it. What you've come back with, some of the answers here, seem to be much more on the nail of simple English, simple explanations. So do you think these AI tools will become the standard query engines in the future?
Good question. I don't see it quite that way. The way I see large language models, and we will look at a different type of large language models in the demo, but the way I see large language models is as a tool. Now, if you see or watch experts use them, they don't just ask one question, get the response, and that's it. It's an iterative process. They'll ask a question, get the response. They'll ask a follow-up question, maybe digging into more detail about one particular aspect. They'll get that response, and they go on to backwards and forwards. And it's very much an interactive, multi-prompt interaction. So I'm just doing single questions here, but that's not really how the smart people make use of them. It's a tool designed really to try and trigger learning to help you. But at least in my book, it's not trying to give the answer to anything. After all, this is a bunch of trained weights. Yeah.
I think it's useful to note that Chrome, if you use Chrome, it comes back with a Gemini answer now at the head of the return response actually already.
Ray, you got your hand up.
Yeah, sorry. Just the context is if you ask it more, what I would call more factual things, like, for example, doing a tax calculation, is it better or worse than more softish stuff?
Yeah, my personal experience, because the large language models that we've looked at today are just trained weights, they tend to be fairly poor at maths. However, we'll look at this in a minute. There is a new type of large language model called a reasoning model, and they tend to be better at the maths. And I've got one running here. We can look at that.
Okay, thank you.
Neil.
Just a quick follow-up on some of one statement you made recently. So what is the limiting factor on the hardware for your home system? So are you running out of DRAM or running out of SSD, or what's the issue? Why can't you run larger models?
Yes, so to run these large language models, you have to do an awful lot of these basic sums, this multiplications and additions and so on. And if you've got, let's say 2, 3, 4 billion weights, then that's not really an issue for a desktop with a GPU like mine to handle. It can do that. If you've got 10 billion, 20 billion, 30 billion weights, You just cannot do that. So those 20, 30 billion sets of very simple sums in parallel over a large number of layers in a reasonable amount of time. So it's computational power is probably the thing. Secondly, it's memory. And in particular, if you're running something on a GPU, because that's good at these fundamental sums and can do lots of them in parallel, if you're using a GPU, what you have to do is to take your model in memory, transfer it to the GPU's memory, ask it the question, then you transfer the model back. So you get this bandwidth limitation between your GPU and main memory as well. And also the amount of VRAM your GPU holds limits how much of a model you can put in and handle at any time. So it's quite a complex sum. It's not, bigger is always better. This
is where the NPU systems are coming in.
Yes, yes, that's right. NPU is really a more focused version of a GPU. And it's just some silicon that's pretty good at some very simple maths, but can do lots in parallel.
Okay, thank you.
All right, I'm going to try on a bit with this demo, but feel free to put your questions up. But here's another sort of like a reasoning type question. I have 10 apples. My friend took 2. I bought 5 more apples. How many apples do I have now? So this type of question involves verbal reasoning. You've got to understand sentences and also a bit of maths. Again, we're sticking with the same model. You can see it's a bit struggling, but with this, look, there we go. And again, you can see the way it comes out is the large language model is going around in its cycle. Now, we had a poem before. Now, one trick for prompt engineering is to add additional bits of instructions, if you like, on the end. So instead of write a poem about hope, we'll also add use only short words. And if we do that, we get, a poem using only short words. Now, there is a technique called role prompting. And what this is about is it's asking the large language model to pretend to be something else. In this case, you are a highly intelligent retired scientist. Describe the advantages and disadvantages of joining the U3A. And it gives you the answer in the format that a highly intelligent retired scientist might phrase a response. Now, I'll do a more fun one. I need a new, not that one. Oh yeah, new context window here. So you'll like this one. You are a pirate. How far is it from England to France? So again, now you are a pirate is me telling the large language models to pretend you are something that you're not usually. Or me hearty, you'll be asking how far it brings. Well, matey. And, so you can use these techniques. You can get it to be British English rather than American English. You can ask it to be, a French aristocrat or whatever you need to do. Some other examples. Chain of thought. We'll have a new context window. Why not? So here's a question, and sometimes this gets it wrong, but for the purpose of demo, who lived longer, Elvis Presley or Mozart? Now, of course, the ages of these characters would have to be in the training data. And it's got an answer here. But what we can do is we can ask the same question, but with a little bit more. Let's think this through step by step. And this is called chain of thought. Give me more information about how you're working out. And let's break it down step by step. Did it come up with the same answer? Mozart lived slightly longer than Elvis Presley. Elvis Presley lived longer than Mozart. These are trained weights. They don't always get it wrong. Right, here's another little one. We're going to use a different model this time. Gemma 2, why not? This is a 5.1 gigabyte size file. Right, so I said before that these large language models are not connected to the internet, and that is absolutely true. However, if we want to get it to answer questions about something we provide, something that's not in its training set, there's a trick we can do here, which is what's called a hash prompt. This might be specific to and what this is doing is asking the web UI only to go out to internet, fetch some data from this URL and add it into the context window. So the large language model itself still isn't doing an internet search, but we are bringing in data. Now this is what it looks like. This particular page, it's our online calendar event. So there's a lot of complex formatted data here. So we're going to press enter there. And the web interface now has got that web page and added it in exactly the same way as if I just typed it all by hand. But then we can start to query that data. Maybe list all events. Now, Gemma 2 is quite a large model from Google. So it's going to be a bit slower, particularly on my poor old desktop here. But hopefully we'll get a decent answer in a reasonable amount of time. Okay, so we can see that it's understood that web page. It's understood that it's a calendar, and it's extracted the events from that calendar. And you can use similar techniques to upload a PDF or even like Word documents and things like that and query them. And we can query this. Let's just do that one. I'm interested in trains. What could I attend? Big model. We're getting to the limits now of what I can sensibly run in here. You could attend mini trams, the transport solution you've never heard of. So again, this large language model has recognized that a tram might be considered a type of train, and it's given us you might be interested in that talk. Ray, you've raised a hand again.
Yes, sorry to keep asking questions. Presumably all these models are stored on your hard disk or SSD, and when you invoke the model, it loads it into DRAM.
Now I'll see what happens if I go into the admin here. I've got models, and I can pull a model. So I just type in the model name, and then Olama will download it from the internet. I showed you that.
Okay, so it doesn't store it on your machine, but it downloads it and puts it into DRAM, and then it's moved from DRAM to GPU if necessary.
Yeah, so essentially that's right. So the file is downloaded. Olama opens up that file into local memory and executes it, if you like, runs it. You type a prompt, and it actually runs all the the input and text and doing all these multiplications and additions and so on to get the answer. So that's what Olama is doing for us. So I'm sure you've heard about the 1% Club on television. That's actually quite a good source of questions. So again, I've gone to the Gemma 2 model, quite a big model. And here's a 1% question from the show. Shoe is to foot as glove is to something. Hand, head, or leg. There you go. Straight away, the answer is hand. Here's why. A shoe is worn on the foot, a glove is worn on the hand. Again, I think that's quite a hard question for a machine to answer. I could give you another one. And I've done this talk a few times in various places. There's sometimes a bit of a debate what the right answer of this one is. So you're running a race and you pass the person in second place. What place are you in now? First, second, or third? Nice, concise answer. And here's one that often completely fools large language models. Sometimes I find it gets the right answer, sometimes it doesn't, because we've got this randomization element in. What's the next letter in the sequence? A, Z, B, Y, W, B, or C? The answer is C. The sequence alternates between letters at the beginning and end of the alphabet. Perfect answer. Quite impressive. All right, let's do this one. What is the first number in English that, when spelled out, has its letters in alphabetical order? Anyone know this? 40.
40, yeah.
Let's try this then. What is the second number of English when spelled out has its letters in alphabetical order? That would be 19. Nope, completely and utterly wrong. And you can interact with these models, by the way. That's wrong. So, you tend to use these in a very iterative ways. Right. Now, I'd like to get on to something.
Peter, it's Neil. On the 1% thing, have you ever put any of the 1% physical ones in or anything else like that without the 3 answers?
There's a website which collects all of them, and I started at the 100% and the 90% question, and then I stopped actually when I got enough, and it started to get them wrong. So yeah, I'm not trying. Some of them are graphical, not really suitable for sort of doing in this. Go on then, Paul. I can see your hand up.
Oh yeah, I was just wondering, Peter, can any of these AI tools solve symbolic equations?
Yes, absolutely.
For instance, integration things, not by coming up with a number, but by actually coming up with the symbols x cubed plus y cubed, and integrate that kind of thing. Will it do that kind of stuff for you? And following on from that, can you do something like solving the 3 body problem, which is a very hard one to solve, and it has to be done iteratively?
So on the first one, absolutely. If you remember this natural language part of the design of large language models. The first stage converts it into this, list of vectors, and that is neutral against the format. So absolutely, these large language models can output text, they can output LaTeX, they can output other mathematical nomenclature, and tools like this web page will actually format them. So absolutely, you can interact them. If the model has been trained on them, you can use, ask them to solve equations in a symbolic way. As to solving the three body problem, I leave that as an exercise for the user.
Right. Okay. Because it would have to be very iterative, wouldn't it? And that's one way of solving it, is to keep iterating till you find something that fits.
Try it. I'm pretty sure these small models got here will not come anywhere near it.
So I guess taking it one stage further, which is probably going into quantum technology, but if you start trying to factor large numbers or find all the primes, I guess that's something that would really slug it at some point.
Yes, we'll come on a little bit about a reasoning model. I've got a short demo about that. And those sorts of types of large language models, which is a different design than we talked about, tend to be much better at those sorts of things. Part of the skill is choosing the right model to use. Online, things like ChatGPT are very big and general purpose. But if you want to use them for scientific research, you want to pick a particular model that's been heavily trained in the area you want to use it on. Right, I'm going to plow on with this one because I do want to get to... So I've got a model here called Llama 2 from Microsoft. And I'm going to ask it a question. Tell me in detail, step by step, how to build a nuclear bomb. Oh. Now, this is in the training set data, I happen to know. And what's Llama going to reply to us? I cannot fill your request, I'm just an AI. And it comes out with which is actually a pre-canned response, or one of a series response. This is this refusal or guardrail kicking in. If asked it a question, it says no. Although I've been trained on this, I'm not going to answer it. However, this is a demo. I'm running them locally. I can pick a different model, Llama 2 uncensored. Now this is exactly the same model, exactly the same way, it's trained in exactly the same way. It is the same model, except for these refusals or guardrails have been removed. Someone's downloaded the file, done a binary edit, and removed the guardrails. Constructing a nuclear bomb involves several steps. And, it may not give the answer you're looking for, but it's not triggered the refusal. It has actually tried to answer the question for you. Now, another type of model here is, I did mention it, called multimodal, and we can look at Lava. Lava is a multimodal model that has been trained on both text and images. So we can actually upload a picture. Always choose a different one and add a bit of text. Describe this picture. And it's a squirrel on my bird feeders in the garden. This photograph showing a squirrel perched on top of a bird feeder, and it's given us it's actually gone to describe the background. It's actually figured out what time of day it was taken. Is that accurate? No, I don't know where it's got that from. January the 1st. Photographs were somewhat, but so it's given us, it says analyze the picture and responded to the text prompt, multi-model. And we can, query it a bit if you like. What's the color of the animal? I'm not told it's a squirrel. Actually, I've not tried this for a while. The animal in the photograph picture grey, which is typical for squirrels in many parts of the world. Now, here's something a bit new. We are going to get a new model called DeepSeek R1. And this made the headlines, not so far away. DeepSeek is from China. It's a Chinese model, and it's an example of a reasoning model. Now, that works a bit differently to the way we've described so far. And what reasoning models do, it comes up with several proposals of what the answer should be first, and then essentially picks the right answer. So it sort of looks like if it's thinking, it's not really, it's just coming up with lots of possible responses. Interesting thing about China, before anyone asked, is Chinese tend to open source their models. So their models you can tend to download and use yourself. You can't use them commercially, but you can use them and play with them like I'm doing now. The Americans tend to be a lot more closed source about their models. So why is the sky blue? And this is this type of reasoning model, DeepSeek. We'll try that. Let's see what we're going to go. So it's going to go, gives us a lot of quite verbose ways to looking at the same problem. It's going to go through several different. It's thought about rallies. Now it's thinking about water vapors. Now it's thinking why the sky isn't black like space, and it's going on further and further. And these type of models do take longer to produce the answer, but they do, keep going at the same sort of rate. And eventually, after going through several different possibilities, it's going to choose the answer for you, kind of in a different way to do them. And this thinking stage, you can either choose to see it or not. If you choose not to see it, then you get nothing for a long time, and then that answer. Ray.
Yes, sorry. The data for that DeepSeek, is that as per the original Chinese data set, or is it a different data set?
No, this is downloaded. It's exactly the same model that the company who released it, whose name escapes me for the moment, has made it open source. There's a website called Hugging Face, which is a very popular place to store models, training data, benchmark results, and so forth, which is kind of interesting to explore.
Sorry, what's it called again? Website?
Hugging Face. The slides that I've got, the last slide has got a lot of references on it.
Oh, right, okay.
If you want to follow anything up, grab the slides from the website and look at the last slide.
What about guardrails in this model?
Yes, there are guardrails in, but not the ones that you expect. You can ask questions about Tiananmen Square and such like in Taiwan and get reasonable answers.
Oh, okay. So it's not quite the original Chinese one then.
So this is a small version of the model, which is open source, which you can run locally. If you want to do any big, serious work, then you need big, powerful computers, which means some server needs to host them for you, and that's why you got, OpenAI on the web and so on. So the equivalent of ChatGPT in China that runs DeepSeek, which would be a very big model, and for the Chinese audience, will have guardrails which are not appropriate for the Chinese reason. But bear in mind, so here's the thing. One thing I realized is, here's a good way to put it. So a while back, I was working in a company and John Cleese came in and gave a talk. And you may or may not know, but John Cleese, as well as being a comedian, certainly used to do lots of working in industry types of talks, time and motion type studies and that sort of stuff. He's kind of quite serious about training. And he came into my company and gave a talk. And his premise really was that different countries have different perspectives of history. And he asked the audience, put up your hand if you've heard of the Battle of Waterloo. And, all the Brits put their hands up. And then he'd ask another question, who put their hands up, who's heard of this battle in America? And all the Americans put their hands up. The point being that each country has its own perspective of history and presents it and teaches it in different ways and prioritizes it. And the same sorts of things, these guardrails tend to be different in different countries. Absolutely, the Americans will also censor your questions and answers, and so will the Chinese, and so will the British, and so will the French, and so on and so forth. But they'll have these guardrails in a different way, which is perhaps more appropriate, if you like, for the country in mind. David.
Hi, Peter. Yeah, have you tried the 1419 question on other models?
What's the 1419 question?
It's the, oh God, now that's a test. Which number has its letters in alphabetical order?
Well, let's try that. Let's pick the model that seems to be quite good at that. Which number has its digits?
Could be. Good. Let's see if I understand it.
So it's probably not concise enough for the question you're thinking of.
Right. Okay. No, that's kind of interesting. It plays back to the comparison of intelligences. The thing that struck me, certainly the initial LLMs you were talking about, not sure about the later ones, they don't think the way humans do. Right, this thing where you in the sort of the broad, in the they're doing like token completion, but that's not how we think.
No, it's let me stop sharing. Let's open it up again. Yeah, absolutely. Remember, these are a bunch of trained weights. This isn't a taught child or it's not intelligent or clever or anything like that. It's doing some very useful work, absolutely, and give us answer. But to say is it intelligent? Is it clever? Is it smart? Is at least in my view, is stretching the point a bit. And of course, we start to get into philosophy and those all sorts of questions. The more you think about these sorts of things.
Well, within the context of LLMs, the first model you ran with that question about numbers in alphabetical order, it didn't check its answer.
No. So the basic large language models, the designs that we talked about, which has very simple layers, okay, it's not complicated. They start outputting the first token, the first word, immediately after the first cycle. So you start to see the answer straight away. And whereas these reasoning models go through that process several times first.
Yeah.
It tries to, they call it reasoning, but it's, I don't know, it's not quite the right word in my view. It's not really reasoning. It's just going through some.
Would you say it's iterative?
Yes.
Yeah. So you would expect it, right? Because it didn't come up with the same answer. If it had come up with the same answer as the previous one, where it said the second number is 19, which is patently false, you would expect if it's iterating and testing, it would recognize that it was the wrong answer.
Yeah, I mean, we can try that if you like on the reasoning model. Let's go back to sharing. So if we have go to the reason model, that was a 1% question, wasn't it?
You ask the 40 question first, don't you?
Yeah, what's the first number in English that when spelt out has its letters in alphabetical order? So this is a DeepSeek, which is a reason model. It's given us
oh boy, it's doing
Doesn't
It's every number.
yeah, sorry, I was going to say, doesn't Perplexity Pro do something like this?
probably, yeah. Oh, hang on.
It's got the answer.
One of the problems I found with DeepSeek, particularly the small models, is they can go on forever.
That's because it's iterating, isn't it? It's trying to refine it.
Yeah.
Oh, nearly there.
Yeah.
Okay. It's performing better than the first one.
Hasn't got the answer yet.
Yeah, it keeps saying
Okay, right.
It's got it. 40.
Yeah, it keeps coming up with 40. But then it keeps wanting to check itself, you see. So it's
Yeah,
still
I'm going to say, it goes on. Yeah.
It's got the answer, but it seems to not remember itself. Not remember it's got the answer. It can't reason it's got the answer, can it?
But it's
Yeah,
probably going through all the other possible options until it decides that's the answer. Isn't it?
it's using what's called brute force.
no, it's doing much better than brute force. It is actually, I hate to use the word, but it is thinking about it.
It's checking.
Checking, yes. But yeah, it does. I think DeepSeek with larger number of weights, things I can't run on my laptop, are going to do significantly better and actually end quicker. But this may go on forever. You've broken my machine.
No, it's getting there. It's getting there. It takes a fair bit of time. So it's going now. It's got 40 again. So it's got to do 31 and 21. I don't know.
It's when it finds out the other 200 options as well.
Okay, it's got 40.
So basically, if you want to perform a denial of service attack against the Chinese supercomputer, this is the question.
Yeah. Any other questions?
Peter, can I ask, do you think that generative AI will ever be able to do deep logic, like first order predicate logic? 50 years ago, I studied it as a student, and we were told that fifth generation computing was going to be the thing, but it all came to nothing because it didn't perform and there were memory problems.
Yeah, I mean, I don't know, and who of us can predict the future. However, I will sort of partly answer with the way these systems tend to be used best is in an interactive way. So there is a tool. God, I should have looked at that beforehand, which is used to predict how chemical reactions, molecules are going to behave, vaccines, and so on. AlphaFold, that's what it's called. You can actually download it, AlphaFold. So that now use generative AI. And the way people use that to produce new vaccines, so this is leading edge science, is they use the large language model as another part of the team. They ask it a question, they get a response. They ask another question, they dig, and every so often the large language model will come up with, maybe a reaction or interaction of molecules that no one's ever thought about before, and then the human scientists will pick that up and say, "Oh, that's a good idea. Let's explore that a bit more." So it's come up with an answer.
It's done it.
So, dare I ask that?
If you ask the other question, next one.
Oh dear! Another few hours later.
Yeah. Yeah. So we've come to our end of our time slot. 5. So, is there any kind of pending questions? We've got the recording. We've got the forum.
Sub in the chat, Peter.
Oh right, sorry. Good point. Can't even find the chat now. Let's Right. Calculate pi to last decimal place. I have to leave. Are the M series Macs particularly suited for these large language models with integrated graphics, neural and processor memory space? Well, I know. I know Olama is got extensions to use the Apple GPU. It uses the Apple APIs to actually accelerate its learning. So I think Olama will work well on pretty much any Mac that's got sort of like modern day GPUs. What happens with robots walking, etc., or playing tables? I have no idea. Those are physical type things which we've not really talked about today. Aren't all the DeepSeek problems and questions sent direct to Chinese government? In this case, no. I am absolutely running DeepSeek on my laptop here, and there's no links to the internet. In China, with a host of those, I expect absolutely yes. And remember, Chinese have got a different culture. They seem to like or accept governments and large companies knowing about everyone's businesses, where the West has a different point of view of these things. The hard part is stealing uranium, plutonium. Yes, very protein folding. Yes, tools like that AlphaFold I mentioned can help aid, predict how proteins fold. How is DeepSeek different? I think we've covered that. Okay, I think I've covered stuff in the quant. Anything else people want to raise? Paul's got your hand up again.
Yeah, Peter, I don't know if you, because I missed the first part. I'm actually in the car because I'm between meetings at the moment. Was there anything about image recognition? One of the things I would find useful occasionally is to put an image up and say, well, what is that? And it might be a plant or a tree or something. And secondly, where is it? Is it a famous landmark or whatever? Are AI models any good for that, or is that more of a Google type search?
No, if you've got a large language model which is multimodal, and we did cover that, in other words, been trained on both images and text, you can absolutely do that. And we had an example of that in the demo where we had a picture of my garden, and the large language models identified that. However, you don't need to use generative AI for this. Now, what I've done myself is I use a tool. We did talk about this in a previous meeting. Image, which is a tool to organize photographs. And that has not generative AI, but classical AI neural networks in it, which is used to recognize faces and places. And so in the photo tool, you can go in there and type a text search, like, find all the pictures of Becky on the beach or with a dog and stuff like that. And because the images have gone through the classical neural network image object recognition, facial recognition, you can create questions like that to query your photo albums. Ray,
are you going to put the slide up with all the references on, particularly that funny sounding website?
It's actually, because this is a repeat, it's actually already up there. It's on U3
on the previous recording. Okay,
and my personal website. Any other questions before we sign off? Remember, let me know if there's any topics you want to cover or you want to present. Look at u3a.social, see if you think it's a good idea or not. Fill in the survey. That's going to help a lot. So if there's nothing else, let's sign off and we'll meet up again next month.
Great.
Thank you.
Thank you very much. Excellent presentation.
Great.
Excellent.
Good stuff.
Thank you, Peter.